Find the least cost route through the network. In this problem, 5 units of flow pass through a network composed of 4 nodes and 6 links. 3 units of flow enter node 1 and 2 units of flow enter node 2. 1 unit of flow exits node 3 and 4 units of flow exit node 4. The link flows are represented by variables x, and the minimum flow rate through each link equals 0. The maximum flow rate and cost per unit flow through each link are shown in square brackets next to each link. If, for a similar problem, the minimum flow rate in any link does not equal 0, a transform network can be created by subtracting the minimum flow rate from the minimum and maximum flow rates for each link whose minimum flow rate does not equal 0. Then, the network can be transformed back by adding the minimum flow rate after it is solved. Network flow problems are governed by 2 fundamental equations: the capacity constraint through each link, Xij, and the mass balance through each node, K. The dual objective function for this network is to maximize the sum product of all dual variables and node sources, plus the minimum of a function involving the link costs, dual variables, and link flows. In these equations, the source at each node equals 3, 2, -1, and -4 for nodes 1, 2, 3, and 4, respectively. These values do not change. The dual variables at each node are initially set to 0 and may change as the network is solved. The generalized nonlinear optimization problem asks to minimize a function f of x subject to I constraints g of x equals 0, where functions f and g are real-valued differentiable functions. For an optimal solution, x, feasibility must be satisfied, and there must exist a lambda vector such that the gradient of the Lagrangian function equals 0. Since the network we're dealing with is linear, and linear problems are a special case of convex problems, no duality gap exists, and the primal objective function will equal the dual objective function at optimality. In this problem, we'll implement a relaxation algorithm which maintains the link capacity constraint and relaxes the node mass balance constraint. As the primal variables and dual variables are adjusted, we'll know we've reached the optimal solution when the surplus of each node, represented by the g vector, equals 0. Once this occurs, we can check to see if the primal and dual objective functions are equal to each other. Let's put the given data into a table and assign the initial link flows values of 0. Already, we have satisfied the link constraint equation because all link flows equal 0 and 0 is the minimum capacity. However, the node balance constraint is not satisfied for any of the 4 nodes. For example, at node 1, there are no links delivering incoming flow and outgoing flow equals 0 plus 0, and the surplus flow is positive 3. Therefore, the surplus at node 1, G1, equals 3. The surplus at nodes 2, 3, and 4 is 2, -1, and -4, respectively. If we expand our table, we can include the dual variables, which we'll also call the node variables, the surplus, g, which we just calculated, and the state of the link, which we'll determine momentarily. In this table, P sub I and G sub I refer to the upstream node, and P sub j and G sub j refer to the downstream nodes of each link. The state of each link can be determined based on the link cost, C, and the dual variables, Pi and Pj. If Pi minus Pj is less than Cij, then the link is inactive and the flow is 0. If Pi minus Pj is greater than Cij, then the link is active and the flow is at its upper limit. If Pi minus Pj equals Cij, then the link is in balance and the flow can range between its lower and upper limits. Graphically, if we plot the dual variables Pi minus Pj on the vertical axis and the primal variables xij on the horizontal axis, all links must be somewhere on the red line, where the inactive region is represented by the first vertical segment on the graph. The active region is represented by the second vertical segment on the graph, and the balance region is represented by the horizontal part of the graph, including endpoints. If we look at the first link, link 1, 2, we notice Pi minus Pj is less than Cij. Therefore, the link is inactive. 5 of the 6 links are presently inactive, like link 1, 2. However, link 3, 4 is balanced because the link cost is 0. With the state of each link entered, we're ready to begin solving the network. With all flows shown in red, we notice nodes 1 and 2 experience a positive surplus, meaning more flow enters the node than leaves. Nodes 3 and 4 experience a negative surplus, meaning more flow leaves the node than enters. The algorithm explained in this example will find the least cost method to route the 5 units of flow from nodes 1 and 2 to nodes 3 and 4 based on the node prices and link constraints. To begin, we'll assign a set of labels L equal to null set and a direction vector set S equal to null set. Then we'll choose a node whose surplus g of k is positive, such as node 1. If no such node can be found, then the network is either optimal or infeasible. The next step is to add the chosen node to the label set L. So the label set now includes node 1. The next step is to compare the label set L and the direction vector set S. Next we select a node I, which is in the current label set but not in the direction vector set, which for this case must be node 1. The direction vector set is augmented with node I, and we continue to step 2, where we calculate the directional derivative y prime for the dual objective function for nodes in the current set S. This equals the sum of the upper bounds of all links entering a node I contained in set S coming from a node J not contained in set S for active links only, minus the upper bound of all links leaving a node I contained in set S going to a node J not contained in set S for active and balanced links only, plus the sum of the sources at all nodes in set S. The reasoning behind specifying only active incoming nodes is because the dual variables for all nodes contained in set S can be increased a certain amount such that all incoming links will still flow at their maximum link capacity. And for the second term, it is assumed all balanced links flowing out of set S flow at their maximum capacity. Since there are no active links entering set S, the first term equals 0. Since there are no active links exiting set S, the second term equals 0. The sum of the sources to nodes in set S equals 3, which makes y prime equal to 3. Since y prime is greater than 0, then increasing the dual variables for all nodes in set S will increase the dual objective function, which is what we want. Changing the dual variables is sometimes called price changing. This step also involves changing balanced link flows entering or exiting set S and increasing the dual variables for nodes contained in set S. Let's first look at the link flows. Since there are no balanced links entering set S or exiting set S, no changes need to be made in the link flows at this time. The dual variables for all nodes contained in set S are incremented by a quantity gamma, where gamma is a function of the link cost and dual variables for all inactive links flowing out of set S and all active links flowing into set S. Plugging in the variables for the two inactive links exiting set S, gamma equals 1. Therefore, the dual variable at node 1 is incremented 1, and the dual variables at nodes 2, 3, and 4 remain unchanged. Returning to our table of values, after the first operation, P1 increases from 0 to 1, and link 1, 3 changes state from inactive to balance. Next, we start over. Clear out the label set and direction vector set, and find a node K with a positive surplus. As before, we'll use node 1. Since set L and set S are not equal, we'll add a node I to set S as before. Next, y prime is calculated and is still positive, equaling positive 1. Since there is only one node in the set, we skip step 3, flow augmentation, and go to step 4, price change. We set the flow in balance link 1, 3 to its maximum link capacity, 2. Now, the surplus at node 1 is only 1 because there is only one more unit of flow entering the node than there is exiting the node. So G1 changes from 3 to 1. Similarly, the surplus at node 3 needs to be updated. The inflows minus the outflows plus the supply equals a G3 of 1. Next, the dual variables for all nodes contained in set S are incremented by quantity gamma. This time, link 1, 3 is not considered because it is in balance. So, gamma equals 4. And the dual variable at node 1 is incremented and equals 5. And the other dual variables are still 0. Returning to the entire table, the changes recently made are shown in red. Since the surplus in at least one node is non-zero, the network is still not solved. Once again, we start over, and we'll select node 1 for K. And as before, both sets L and S contain node 1. But this time, when calculating y prime, the value is negative, since both links exiting node 1 are either active or balanced. This means the direction vector, represented by the nodes in set S, would not progress the network towards optimality, i.e. feasibility, if their dual variables were to be increased. Therefore, we return to step 1 and add neighboring nodes J to the labeled set, which can result in a flow augmentation path from I to J or J to I for all balanced links I, J, whose flow is less than max capacity, and all balanced links J, I, whose flow is greater than 0. Under such conditions, node 2 qualifies because link 1, 2 is balanced, and the current flow through the link is 2 units less than the maximum. Next, we select a node I contained in set L, but not in set S. Selecting I as 2, and the direction vector set S now includes nodes 1 and 2. Once there are multiple nodes in the labeled set, step 3, flow augmentation, can occur if a flow path from a node K in the set to a node J in the set is established. The surplus of node K is positive and the surplus of node J is negative, and if all adjoining links are capable of changing flow in the direction from K to J. Since the surplus at node 2 is positive, flow augmentation is not possible for this set at this time. The gradient of the dual objective function for a direction vector set S containing nodes 1 and 2 equals positive 3. This means increasing the dual variables in set S will improve the dual objective function. We'll next check to see if any link flows need to be updated. The nodes in set S and the nodes not in set S are identified, and the 4 links which cross into or out of set S are checked to see if any are balanced. None of these 4 links are balanced. Therefore, link flows are not modified. If A equals active, B equals balance, and I equals inactive, the 6 links are labeled according to their current state, and the only links which satisfy the conditions used to compute gamma are the 2 inactive links leaving node 2, links 2, 3, and 2, 4. So gamma equals 2. The dual variables are incremented by 2 for nodes 1 and 2. Nodes 3 and 4 remain at 0. Updating the table of data, the revised values are shown in red, and link 2, 4 has become balanced. Since node 1 has a positive surplus, we'll initialize the label set to include node 1. The direction vector set also includes node 1, and y prime equals -1. Since link 1, 2 is still balanced, node 2 is again added to sets L and set S. Flow augmentation is again not possible since the surplus in both of these nodes is positive. Y prime equals +2. Since this value is positive, we'll move on to step 4 and update the link flows if necessary. We check the same 4 links to see if any are in balance, and link 2, 4 is now in balance. Therefore, the flow in link 2, 4 is set to its upper bound of 1. Next, the dual variables are increased by gamma. The states of all 6 links are labeled, and link 2, 3 is the only link which qualifies to compute gamma, so gamma equals 2. And dual variables associated with nodes 1 and 2 are incremented by 2. Returning to the data table, the revised values are shown in red. Since the surplus at node 1 is still 1, set L contains node 1 and set S contains node 1, and y prime equals -1, as before. Node 2 is added to both sets, and flow augmentation is again not possible. Y prime equals -1. Therefore, we'll add a node j to the label set such that the connecting link ij must be balanced and whose flow is less than the maximum capacity, or a connecting link ji which is balanced and whose flow is greater than 0. Node 3 is added to the label set because link 2,3 is balanced and not at max capacity. Node 3 is chosen for variable I, and the direction vector set S now includes node 3. A quick check is made to determine if flow augmentation is an option. Since the surplus at nodes 1, 2, and 3 are all positive, flow augmentation is not possible because the second requirement is not met. Next we'll calculate y prime, which equals -2. Therefore, we'll add node 4 to the label set because link 3, 4 is imbalanced and its flow is less than the maximum capacity. Since surplus at node 1 is positive, the surplus at node 4 is negative, and adjoining links 1, 2, 2, 3, and 3, 4 are all balanced and have the capacity to increase their flow in the direction from 1 to 4, flow augmentation is possible. This means the flow through these 3 links can be increased a value of delta, where delta equals the minimum of the surplus of the upstream-most node, the negative surplus of the downstream-most node, the max link flow minus the current link flow for all links flowing in the direction of node 1 to node 4, and the link flow for all links flowing in the direction from node 4 to node 1. In this instance, delta equals the minimum of 1, 3, 2, 3, and 5, which equals 1. The data table is revised once again to reflect this flow augmentation, and the most recent changes are shown in red. Since the surplus at node 1 is 0, we'll begin with node 2 in the label set. After setting I equal to node 2, the direction vector set S contains node 2. The directional derivative of the dual objective function y prime equals -2. Next, we add node 3 to sets L and S because link 2, 3 is balanced and the current flow does not equal the maximum link capacity. Since the surplus at nodes 2 and 3 are both positive, flow augmentation is not possible. Since y prime is negative, node 4 is added to the label set and direction vector set because link 3, 4 is balanced and the current flow is less than the maximum capacity. Since node 2 has a positive surplus and node 4 has a negative surplus, the second requirement for flow augmentation is met. The link capacity in the direction from node 2 to node 4 can increase for both links 2, 3 and 3, 4. Therefore, flow augmentation is possible. The increased flow through links 2, 3, and 3, 4 is the minimum of 1, 2, 2, and 4, which is 1, since the surplus at node 2 is only 1. 1 unit of flow is added to these two links, and the data table is revised. The changes are again shown in red. Since the surplus at nodes 1 and 2 are 0, the label set will begin with node 3, because node 3 has a positive surplus. The direction vector set contains node 3 also. Y prime equals -4, so node 4 is added to the label set, since link 3, 4 is in balance and the current link flow does not equal the maximum link capacity. The requirements for flow augmentation are met once again. The quantity of flow augmentation is limited to 1 unit by the surplus in both nodes. Updating the data table, all node surplus values equal 0, so complementary slackness is satisfied. Looking back at the original network, the final flows are shown in red, and the final dual variables are shown in blue. We can confirm this is the optimal solution by checking whether or not the primal and dual objective function values are equal, since the network is linear and there is no duality gap. The primal objective function value equals 17, and the dual objective function value equals 17 also. When reviewing the possible solutions, the answer is C.